Okay, I think we're ready. We're going to do journal bearings today. So journals, uh, bushings, lubrication. We're not going to do the whole topic. We're going to split this over 2 days. The next version or the next piece of this will be on Monday. Friday we have exam 3, so we won't be streaming anything on Friday. Let's first, before we get too far, let's go clarify what a journal is, because it might be something that you haven't named before. You've seen it, at least in pictures. You may not have named it before, though. So I've got one I downloaded from McMaster. So this is a kind of average type of journal. There are many different types, but this one kind of represents a lot of the different pieces. The part in the middle, this is the journal. So the shaft part is the journal, and then the part that moves, well, actually, usually this part stays still and the shaft moves. I just can't really show you the shaft moving, spinning, because it's a circle. But the bearing is a sleeve. Sometimes there are little grooves inside here for oil and lubricant to get around in, but there's no rolling element. So this one doesn't have any tolerance at all, but there's a tiny, super tiny gap between the journal or the shaft and the bearing, this gold part, the sleeve, like thousandths of an inch. And that really tiny gap is filled with some type of lubricant. Most all of these lubricants are liquid, and they're an oil of some sort, a fluid. I said fluid, and that does include air. There can be air-filled, some kind of gas-filled journal bearings, but most of them are going to be an oil of some sort. And sometimes the bearing, the sleeve in here, is called a bushing. It's usually pretty straightforward, as in it's just a sleeve, just a hole, and then like I said, there could be some sort of openings for lubricant to get in there. Sometimes the lubricant, the oil, sometimes it's pressure fed into these bearings, and that would be called a hydrostatic bearing. Sometimes, and those are usually for really low RPM, so the shaft is turning at a slow rate, and so since the shaft is turning at a slow rate, it doesn't spin fast enough to generate pressure in the film, the fluid, and so you have to pressurize that fluid. Other times the fluid is just there, and sometimes it's delivered under low pressure, and those are hydrodynamic bearings. Sometimes the fluid is not in a setting like we're looking at here at all. It's between two gear teeth, and they're just kind of trying to keep the gear teeth from ruining each other. That one falls into elasto-hydrodynamic category. There are occasions where, maybe on purpose or not on purpose, the fluid gets very thin. So the shaft has heated up the lubricant somehow, and its viscosity has dropped, and the thickness of the fluid is smaller than it normally is. So normally, we're talking a couple of thousandths of an inch, but maybe it's gotten down to a couple of molecules thick. So that would be a boundary condition, is how you would talk about that. And then there are other cases where the tolerances are so tight and the temperatures are so high that you actually use a non-liquid lubricant, so like graphite or something, and that would be a thin film lubricant. So what we're going to talk about for pretty much now on is the thick film lubricants, so oils and things like that, and they're going to be in hydrodynamic settings. All of these are described in chapter 12, chapter 1, or section 1, all of the 5 different ones. But the one that we're going to focus on is basically what we're looking at here. You've got a journal in some kind of sleeve bushing, and the gap is small, but it's thick compared to what it could be. It's more than molecules thick. So it's a thick film fluid in here. I did bring up some pictures of what we might be dealing with. So you might ask, well, why don't we just use the roller bearings that we were talking about before? last time. And some of the times you can, maybe the application will handle a roller bearing. It could be more expensive, but it could also not suit the design. So a lot of times when you're going to use one of these journal and bearings, journal and bushing, it's because there is such a high impact load that if you imagine like a car engine, I have some pictures here for a second about a car engine where the crankshaft, let's see, this is a crankshaft. So this piece the guy is holding here, this crankshaft has to endure thousands of explosions, reactions to explosions, every minute. And the impact of those explosions could deform or cause one of the balls in a ball bearing, a roller element bearing, to deform or deform the race that it's sitting in, just constantly getting impacted. And so there are situations where the roller element bearing just isn't going to survive very well. So this crankshaft, obviously this looks like, it's not straight. There is, if you notice, there are sections like this piece, this one, this one, this one, and this one. They're all aligned, and these others are offset somehow. So if you don't know anything about car engines, that's okay. That's not the point of what we're doing. Let's see if I have another picture here. Here's a crankshaft closer up. So these surfaces, the ones that are aligned, these are the main journals, and they are very precisely aligned, and they sit in, well, let's see, here's one. They sit in these little bushings or these bearings, these main journals, and all of this has to be, aligned down to the sub-thousandths of an inch, possibly in some settings, depending on, what performance engine you're building, but thousandths of an inch. And you can kind of see these inserts here, and they have grooves in them. So there's a little groove. They have holes in them. The grooves in the hole are for oil delivery. Obviously, or at least I assume you have to put oil in your car. This is one of the places it goes, is to lubricate these journals and the bearings that they're riding in. These inserts are a soft material, at least compared to the journal. The journal is super polished on the crankshaft areas where it's going to ride in these bushings or these bearings. It's also polished on these. The pistons themselves will connect to these offset sections of the crankshaft with similar journals. Just they're not aligned. They're offset so you can develop the torque you need when the engine is running. So this would be an application where you would see the journals in action. And the journal would be here, 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 and let's see, which one is it? This one here. And they're going to sit in these locations in the bottom end of an engine. And this is one of the locations or one of the applications where you would have these high impact loads that really wouldn't make sense for putting roller elements. The other reason you might not want to put a roller element in here is how are you going to get it in there? This crankshaft is all distorted. It's not a straight shaft like you would have on most shafts that we've been talking to up until this point. And so you couldn't actually get you'd have to make them as part of the crankshaft. These crankshafts are one piece, either forged or cast, or depending on, most of them are cast and then ground, but there are forged ones also. But you couldn't get a roller. You get one on this end, and that's it. All these others, you couldn't actually get a roller bearing around them without splitting it apart and putting it back together. So that's another reason why you might not be able to use a roller element bearing, is it just doesn't, you can't assemble it. And so you need another type of bearing. All right, so that's kind of what we're talking about, that style of thing. Now, we won't really spend much time on crankshafts in particular. Actually, no more time than we already did on crankshafts in particular. Most of the things that we talk about will be this style where it's just a shaft in a sleeve. We're actually going to start, and your book does this too, in chapter 12. We're going to start with an older version of the equations that people were using to discover how these things were working. Your book does this because the older version of the equation is not applicable anymore because it makes a kind of fatal assumption, and they might have done that on purpose. I didn't go research how this is Petrovs Equation, so how Petroff decided to do this. But a lot of times you'll see, sometimes on purpose, there's a assumption made just to get past a part in a problem, and maybe it was also that it wasn't known that it needed to be made. But either way, this equation that we're going to look at, the derivation of it is correct. There's just this one assumption that the shaft, the journal, stays concentric with the bearing. That isn't true in the real world. Now, he does go through here in the derivation of it and talk about the shaft being vertical. And in that case, maybe there's less chance of the shaft being eccentric with the bushing. But in general, you can't count on that. Even with these super tight tolerances, you can't count on the shaft being, or the journal being concentric all the time. So that makes the use of the end result of this equation not quite right. But the equation does go through and describe all of what's going on, and it does describe how you would go about analyzing, couldn't say that word all of a sudden, analyzing a fluid filled bearing like this. Also, it sets us up with some dimensionless constants that will be used for what we actually do. We're going to spend a lot of our time in charts that describe different ratios of what's called Sommerfeld's number and how it corresponds to radial clearance, or the oil flowing out of the side of the bearing, or all kinds of different things. But all these dimensionless constants can be seen in Petrovs equation. So before we do Petrovs equation, let's just mention, your book does this later, but let's do it now because it kind of helps. Let's mention, I'm trying to find the picture in your book. Here it is. It's actually 12.6. So hydrodynamic theory, it shows this picture and there's a little description here. It's interesting to read, but what they're doing here is Beauchamp Tower is working with the railroad company, and he is trying to find a better bearing setup because, a railroad car has huge amounts of force that have to be supported on the wheels. And so he's trying to figure out a better way to do that with these bearings. And so he's doing some research, and he has a journal. So this circle is the shaft or the journal, and he's got a bearing. He's got some lubricant down here, and he's spinning the shaft and putting force on this bearing to simulate the weight of a rail car. And maybe he wants to see that what's going in here. Maybe he wants to drop in more lubricant or something, but he ends up drilling a 1/2-inch hole up here. Let me zoom in a little. So right up here, he drills a little hole, and I don't know why he drills a hole in there, and I don't think it even says. Maybe if you went and did, there's a footnote down here. You can kind of see it. If I can get it on the screen, maybe if I move the camera, that would be simpler. There's a footnote about where this comes from. But I think maybe he wanted to drop more lubricant in there, or maybe he just wanted to see what was in there, because it's a 1/2-inch hole. If we just want to drop some lubricant, it wouldn't have to be that large. But anyway, it does say drilled a lubricator hole, so maybe he did want to add lubricant. Anyway, when he drills this hole and spins it up, he notices this fluid in the bottom, the oil that he has in the bottom, starts coming out of the hole that he drilled. And so he's like, well, that's no good. I just wanted to, put lubricant in there. So he plugs this hole, puts a cork in there, like a wine cork or whatever, and it blows the cork out. And now he's interested because, okay, now I've got some kind of pressure in there. So he puts a wooden dowel down in there that, he thinks that'll keep it, and it blows that out too. And he's now at the point where he's realized that there is a pressure in the fluid, the oil, the lubricant, because this shaft is spinning, and so he keeps doing more and more research. And so that pressure in the film is what we are going to be interested in, because developing that pressure is what keeps the journal from actually making contact with the bearing, whatever. This is a half bearing, but most of the bearings that we'll deal with are full circle, bushings. But that pressure is the key. You don't want to have metal of the journal touching the metal of the bushing, or whatever material the bushing is. When you have that contact, it's almost always going to lead to a failure. Now, there are some bearings that are non-fluid filled. So there are centered bearings that have metal with lubricant built together. And so the lubricant is actually in the bearing. There are other bearings for, low load applications that are Teflon or nylon type materials, where it's just a low friction material. And so the lubricant is almost the bearing itself. So there are applications where you don't have actual oil in between the journal and the bushing. We're not really talking about those. Those are really for low speed or low force type applications. So we're talking about ones where you need a barrier, some amount, even if it's a thousandth of an inch barrier of lubricant. All right, so now let's do Petrovs equations. I've got my circle templates out because we end up drawing a lot of circles. This is, your book does go through this derivation, and we're just going to kind of walk through it, and then we'll look at, depending on what time it is, we'll look at where this might take us next time. Otherwise, we'll just pick up next time with the actual way that we're going to use this thing. So today it's going to be a lot of just equations and a lot of description of where these equations are coming from, because the description is correct. The only thing, or the main thing, that is the problem with these equations is that they do make the assumption that the journal and the bushing stay concentric. In fact, I think there might be some pictures, diagrams. There's a couple here. So here is the one. Oh, it was already on there. You can kind of see, this is kind of where they use they're deriving Petroffs Equation. So there's the journal, the dark shaded is the lubricant, and the outer circle is the bushing, and then they have a side view of it. And they're assuming that this case stays concentric, where in reality, now this is exaggerated, but you're going to have the journal offset to one side or another. And again, this is a very much exaggerated picture. Your clearances here are much, much tighter than this. But the point is that the journal does offset from being concentric with the bushing. So that's why these equations won't work on their own. We need charts and things to help us. All right, so let's start with a picture. Zoom out. And let's start with just setting up what is going on here. So this is going to be the inside of our bushing. And again, we're going to make this concentric as I can draw it anyway. This will be our journal. Let's make our journal, I don't know, some color. So this is our journal. And between the journal and the bushing, that's where our lubricant exists. We can have some orange lubricant in here. So all of this gap is filled with oil or whatever kind of lubricant we have. And then the rest out here is mounted to our machine, whatever our machine is doing. It's held solid. All right, we're going to need a speed. A lot of times in this kind of setting, the speed is a RPM, and for RPM we usually use, let's use a red. Where'd my red go? So here's our N, capital N, is going to be the speed of our journal in RPM. The journal itself has weight, plus it's probably supporting some kind of weight. Like if you think about the crankshaft, it's at least supporting the weight of all of these pistons and connecting rods that are on it. Plus, occasionally there's these impact loads. So we're just going to represent all of that with a W. It's going to be the weight here. Let's see, what else do we need in here? Your book has, well, it flip-flops between H and C. And what these are the clearance. We're going to use C, but I think your book does have some instances where it's using the letter H. But this distance right here, that is C for clearance, is what it'll end up being. But like I said, I think there are some cases where it starts with an H. We're going to use C for clearance. But your book is going to start with an H there. What else do we need? Well, I think that'll get us set up for now. The journal obviously has some length into the page. We'll just call that L. A radius. It'll need a radius. We'll use an R for that. Maybe we can put that in here. So we use an R for the radius. And I think that'll get us most of the variables that we need. There is one other thing that we need to talk about though, and that's going to take, we need to kind of zoom in on this section so that we can actually see what is happening in the fluid. So if we zoom in close enough, the journal just is going to be a straight line. We're zooming in really close. The bearing, you know, the bottom surface of the bearing is going to be another straight line. So down here's the bearing. And I'm going to switch between calling this a bearing and a bushing or a sleeve, all the same thing. So this is stationary. And this is moving. We have it as moving at n RPM, but this surface here has a velocity. We'll call it U. So it'll be the velocity. So like the surface velocity of this shaft, but we're zoomed in really close, so it just looks like a straight line. And in between here, we've got our fluid, whatever it is, the oil. So this fluid, where it's touching the bearing, well, I guess we could use that orange again. Where it's touching the bearing, it kind of adheres to it, and it has no velocity. So here, the speed, or the, I want to use a little u, equals 0 meters per second or inch per second or whatever. Up here, the fluid adheres to the journal, and it has some velocity. So the local velocity for right here is u equals whatever the velocity of the journal, surface velocity of the journal is. And then all between here, I'm going to draw dots. Your book draws, I think they draw this picture. Maybe they don't. Oh, they do. They draw it earlier on page 611 when they're talking about viscosity. They draw little rectangles. I'm just going to draw dots for now. The rectangles might be more appropriate. They're just harder to draw quickly. So we're going to use circles. These are rectangles in your book. So what happens is the fluid, if nothing's turning, the fluid velocity is all equal because this velocity is 0. This one's 0 because it's part of the mounting of the machine, so it's not moving. And so all the little dots are lined up, sitting at 0 velocity. But then once we spin this journal, the shaft, then these start taking off. And so we're at a point now where it's kind of at a constant speed. We're at a steady state. And there's a distribution of speed in this fluid. And it's causing a shear. you know, if we think of all of these as layers in the fluid, each one of these little layers is sliding past one another, which creates a shear stress. And your book describes this shear stress with tau, so the shear stress in the fluid is equal to this slope, which you could use du dy if we create y as, you know, this direction. And it's proportional to this. It's not equal to this. There's some proportionality to, you know, how steep is this slope. And they use mu for that. So this mu is absolute viscosity. And this du dy is the slope of the line that I've drawn here, a line of dots. So it's the slope of the speed of each one of these dots as we move from y equals 0 to y equals c. You know, this clearance is c right here. And so that's where we're going to start. This is where your book starts also. So I'm going to do this, try to write all these equations in MathCAD so that they are hopefully easier to read and we can organize them better than kind of scattering them around. We'll come back to this page every now and then, but most of the time we'll be over here. Maybe I can put, I don't think I can put it over there. Huh. All right, should have thought about that. We'll put that over there. All right, so we've got our equation that we just derived, well, not derived, but explained. So this is Newton's, like a, what is it? It's for Newtonian fluids, but they had a particular name for it that I don't recall right now. Newton's viscous effect. That's what it is. And so we're starting there. And we're going to take, the first thing we're going to do is we're going to work on this du dy. If we think about our picture again, all that is the slope of this line. If this point is 0, y is 0, and the velocity is 0, then we have a 0 here, and the slope of this line is just u over h, or your book uses h, but it's going to end up as a c, because the c and h are the same thing. So the slope of this line is my velocity of the shaft, surface velocity u, over c. So let's do that. So tau, I'm just writing these as symbolic equations. We're not trying to actually solve anything. I just want it to be clear. Viscosity times, let's put in a d. But now we're going to have, well, actually we don't even need the d. We're just going to use u over, and I'm going to go ahead and put the c. I think your book does use h for a while. All right, and c is radial clearance. Now if I take this equation and operate on it, so I'm just going to multiply, oh wait, I got to do this. Multiply both sides by r. R is the radius of the journal. So that will give me just tau times r, and all of this other side, mu times velocity over c times r. So that doesn't seem like it does a whole lot, but we can also think of the definition, not this definition, but the definition of shear stress in general, which is tau equals V. A lot of times you use a V for shear force. I'm just going to use F because it's still a force, but the F will make it easier to do something later. So that's just the definition of shear stress, force over an area. In this case, we're thinking of the force being the shearing force in the fluid and the area being the area of the fluid. All right. So I can take this definition, plug in for this tau, and that gives me F over A, still times R. Well, let's put the R out this way. And then the whole other side of the equation doesn't change. Let's just copy that. All right. So all we've done is multiply both sides by r, subbed in a definition for shear stress, and now we're at this point. Okay. Now what I can do is start to figure out what this area is. So we might need to go back over here. So the area is the surface area of the fluid. And we want the surface area, now again, it's this clearance, this C is 1/1000th of an inch or so. So we're talking about really essentially the same area here and here, but I want the area on the surface because that's where my maximum velocity is. So the area of this surface is basically the area of the cylinder, but it's however long the bushing is actually. So it's the area of the cylinder that overlaps with the bushing. So if we look at our SolidWorks, where's our SolidWorks deal? So it would be, I'm not going to be able to show it too well, but let's look at it head on. So it would be this area right here, right? That length. Obviously, the journal itself can extend past the bushing, but it's the area of the journal that's in the bushing that we're interested in. So that's just the circumference of the bushing times this length, and that's the length we're going to call L. Okay, let's go back to good old MathCAD. So area for us is 2 pi r, and it could be pi d, but we want the r in there for later. So we're going to use 2 pi r. Times the L, we're going to use L as the length of the bushing basically. This force, oh, I'll set that up as a symbolic. There we go. This force is, well, this force times this r, force times radius. If we look at our picture, we're talking about on here, this force times that radius, that's going to be a torque in the end. And this force actually is, I drew it in one location, but it's all the way around the whole thing, right? So there's lots of these little force arrows all around the area, surface area of the journal. So that force times that radius is this torque. So we're just going to sub in that definition. Oh, hold on, did the wrong thing. There we go. So force times radius is just going to be a torque. So taking these two, plugging them in to force over area. In fact, let's just take this whole equation. And for force, we're going to put force over R, or force times R is just going to be a torque. And then area is 2, all this stuff. So now we've got this. We are going to also work on our velocity here. So let's go look at that. Our velocity is the surface velocity of this journal as it's spinning. So it's and again, I've made it a linear velocity right here because we were zoomed in so close that the curved journal and the curved bearing look like straight lines. So this velocity is how fast is a point on this surface moving. So a point, how fast is it going from here to here, for instance. So that is going to be, N is how fast the shaft is spinning. That N is usually going to be in RPM, revolutions per minute. So U is going to equal 2 pi r. So that's that circumference again, times N. And then your units here, you might have to work on the units if you want them in different speed units. But right now we're not so worried with the units. All right, let's go back over here. Let's put in 2 pi r N. for U. All right, now we've got this equation. Let's solve this one for torque. So basically this means moving this denominator over to the other side. So torque equals 2 times 2 is 4. We have a pi squared. We have R, we have 3 R's in there, so R cubed. We have L, only one of those. We have the viscosity mu. We have N. And then all of that is over our clearance. So we're getting somewhere. Oh, again, I set that up not as a symbolic one. There we go. Not like that. Why is it doing that? Well, there we go. Click on the right thing eventually. So now we've got somewhere that we can calculate the torque, assuming we know the speed, or we can calculate the speed assuming we know the torque and the viscosity, things like that. But this still isn't Petrovs equation. So what we need now is one of the things that they were trying to figure out, Beauchamp and Petroff, they were trying to figure out how to deal with this friction, because that's the whole point of the bearing, is to reduce the friction. So we don't even have friction in here, so we're going to use F for friction, and we're just going to I'm going to write out what the definition of friction is. So it's a tangential force. Oh, let me do it. Divided by a normal force. That's the definition of friction, is figuring out this ratio of tangential force to normal force. All right, so that tells me that friction could be written as, let's go back to our picture. Here's the tangential force all around here. We created earlier, right here, an equation. So this equation, if I solved it for F, would say that, well, that force is T over R. Torque divided by R is that force. So we'll put that in. That's the tangential force. And then that's over the normal force. The normal force is W. So it might make it clearer if I had my force F, right here. Force does go all the way around it, but we're going to put this force here, and the normal force is the weight of the journal plus whatever force the journal is supporting. And we're just going to use a W for that. I think your book uses a capital W. Let me see. They do. All right. So now we've got this. So what this says is I have friction in here now, and I have this torque, which I have an expression for up here. So if I solve this equation for torque, I will get that torque is equal to frictional force times the weight times the radius. I also have the expression that torque is this, so I can set these equal to each other. So in other words, I can do this. That equals, whoops, missed it, that. Okay. And now I have a equation, and we're pretty much at Petrovs equation, but there's a little bit of work to do to get rid of a couple of terms like the weight, for instance. Why don't we talk about, let's go back over here. We're going to talk about that pressure that is in the fluid. So if this journal is, trying to push down on this fluid, the fluid is pushing back up on the journal, and there's developing some pressure in the fluid to do that, to support the weight of the journal. We're going to get us a new sheet of paper. Let's actually get our ellipse template, because we're going to try and draw this in 3D-ish. Let's see which one of these is going to work best. Maybe this one. So let's put our something like this, connect them together. And this is our journal. I can't draw the bearing because it would just get in the way. So the journal is surrounded by fluid. The journal has a weight W, and there is fluid all around here. But in this particular configuration, and again, this is kind of one of the simplifying assumptions of how we're going to deal with it, and how Petroff dealt with it. We're going to say that the fluid directly underneath here has to support this weight. We also know that this dimension is the one we're calling L. We haven't ever drawn that one out, so we can draw it now. So our fluid underneath here, we're going to do, if you remember bearing stress from last time you did bearing stress, there's a projected area when you're dealing with bearing stress of a curved surface. And so we're basically going to take, let's see, what's it going to look like? Something like this. We're going to take and project down the area of the fluid, and that pressure is on that area. Obviously, this is a simplification of what would really be happening, but we have to, simplify something. So this is a projected area of the pressure or of the fluid that the pressure is acting on. And this thing has an area. This distance is 2 pi. This distance is L. We already drew that in. And then we're just going to call the pressure. So all these little arrows are P. Pressure in the fluid. All right, so that's what we're doing this next step. So to write equations for that, let's do a force balance. Oh, well, maybe we should go back. So remember the definition of pressure and stress is force over area. So therefore this force that has to balance this weight force, P times A. All right. Now we can go back over here. So P times A also has to balance the weight of the journal plus all the forces acting on the journal. We talked about area of the projected area being P 2 times pi times R equals W. So all I did there is substitute 2 pi R, times L. I didn't mean the pi in there. There's no pi, it's just 2R. I'll show you the picture again in a second. I wrote down, I did write down 2 pi. This is just 2 radiuses, 2R, not 2 pi. All right. Now we have a value of W, and we can get this pressure into our equation up here with this W sub in right here. So let's copy this guy. I'm gonna have to create a new page. Paste him in. Let's copy our value for W and put that in for W. And this is Petrovs equation. It's just really messy right now. So, but you can kind of see there are R values all over the place. There are some constants, pi, 4, 2, a lot of different things. Let's rearrange this to a more usable form. And it's going to say that the friction, this is Petrovs equation that you actually would use if you were using Petrovs equation. 2 times, we end up with a pi squared, not to the 23rd. We have r cubed, r over rr. So we end up with just r. And then we're going to put this r over c as a term. We do that so that it's dimensionless, right? Radius over clearance are both inches or both whatever they are. They're both units of distance. So this ends up a dimensionless set times everything that's left. So we have the mu, so that's the viscosity. We have the speed in, and then we've already taken care of the 2, and we have the p. So both of these over p. This set, the units on viscosity, once you get those correct, then they will cancel out with RPM and pressure. There might be some like speed issues here, so revolutions per minute. You might have to, figure out what actual set of units to put in here if you were worrying with it. But all of the units here actually end up canceling out. And this Petrovs equation. Now again, we don't use this equation directly because of some of the problems that it has with the concentric shaft. We did that projected area thing. So there's a lot of simplifications to get to this point, but we do use these pieces of it, R over C, mu n over p. We do use those. And how we use those is if we take and multiply both sides, multiply by r over c. So if we multiply both sides by r over c, then we will have f times r over c. We have that on the one side equals everything here, and we're just going to square the r over c term. So this part gets squared. So this piece of it is called Sommerfeld's number. So S, whoops, that's not S, S equals this term. And this is the Sommerfeld number. We use this all the time for dealing with these journal bearings. And how that works, we actually probably would have time to do a little bit, but I think it'd be better to save that for next time. But this, let me just look at a chart over here. Let's find one. There are a lot of these different charts. These are all viscosity charts. Here's one. So down here, if we zoom in, there is r over c squared mu n over p, Sommerfeld number. It's going to be the x-axis on a lot of these charts. Once we get, here it is over here. Here it is here. Now this chart's actually interesting. Let me have to, can I get it? Yeah, I can get it all on there. Because the x-axis is the rc squared mu n over p. The y-axis, I don't know if you can see it, but it is f r over c. So this is directly relating those two dimensionless terms in the Petrovs equation. And this is trying to get a coefficient of friction out, is what Petroff was trying to do originally. Now you'll notice these graphs are not linear, and this is a log-log scale. So there were some other things that had to be done to actually get to this point from Petrovs equation. We're not going to delve into what has to be done to get from Petrovs to this equation, but you can actually see where Petrovs equation started this process. Another thing we do need to look at, though, is right here. So here's one of those mu n over p. And they've got it set up as greater than 1.7 times 10 to the negative 6. What they're doing here is, well, it says a design constraint to keep thick film lubrication is to be sure that this piece of the Petrovs equation, mu n over p. So mu is viscosity, n is shaft speed, p is that pressure in the fluid. This ratio needs to be greater than, and it's not a large number, but it's this viscosity is a super tiny number, 1.7 times 10 to the negative 6. So they show you this graph over here again, where mu n over p is the x-axis, and they've got this line here representing. Actually, this line is not at 1.7 times 10 to the negative 6, but it is a breaking point in the fluid. So over here, they've got this thin film. So you've got this ratio too small, less than the 1.7. I think this B point is at a even smaller number than 1.7, but there's a factor of safety built in. Anyway, over here, you're in this thin film, and they call it unstable. So this is where the journal and the bearing are just too close together. So maybe you've got a situation like that, where you've got a really tiny gap between the journal and the bearing. Can't move my book in the right spot. So that could be over here. You've developed a thin film if this ratio too small, and that could be a situation where, since there's essentially no fluid, no oil, or not enough oil to transmit heat away fast enough, that it will build up heat instead. And the problem with that is that this viscosity number, for pretty much all materials, once they heat up, the viscosity goes down. So if this number goes down, then this ratio goes further this way. And so it's this cascading failure of heat buildup in the fluid that causes loss of viscosity, which causes more heat buildup because the parts are even closer together, and which causes more viscosity loss. And so you get this cascading failure in this thin film unstable. So that's why they're saying this bearing characteristic needs to be greater than this 1.7 times 10 to the negative 6. On the other side, on the thick film, if you now, same kind of thing happens. You introduce some heat here, and instead the viscosity does drop a little, but it's able to dissipate the heat fast enough that it doesn't cascade. So the drop in heat doesn't reduce the viscosity to a point that it can't support the journal any longer. They describe that in this paragraph right here. Let's see, there's the description of, to the left of the unstable region. Here, we result in a lower viscosity, which is a smaller value of this, which causes, look, on the y-axis is coefficient of friction. So the coefficient of friction goes down, which actually makes it easier to drop the temperature in the fluid instead of increasing the temperature. But that only happens if you have enough fluid in that location to actually dissipate the heat away. If you don't, you have a thin film location, then eventually you have the journal touching the bushing, and metal on metal is not going to be good. I think that's probably all of the intro stuff we need to talk about. There's a few minutes left, but not enough to actually go through and solve any of the equations that we're going to do with this. So next time we'll pick up with how do we use these things using Sommerfeld number and all of these different charts here. They're really straightforward, and they tell us a lot of information. They can tell us the minimum clearance. So what is this minimum clearance? The location of it, how much fluid is flowing through there, the pressure in there, the friction. It can tell us a lot of things using this one Sommerfeld number and all the charts around it. We'll do that on Monday. On Friday, like I said, we have the exam. So the exam 3 works exactly like exam 1 and 2 as far as, well, it's in Moodle. There are 15, 16 questions. Some of them are partial credit. You'll upload your written work. It's exactly the same as the others. Same amount of time, 75 minutes. So if you've taken exam 1 and 2, then exam 3 is the same thing except about springs. It's all springs. If you have any questions, let me know. I think I'll let y'all go now. And send me questions about the exam or about this if you're ready for moving on to some of the bearing calculations. And we'll pick back up on the bearings on Monday. See y'all later.